Hello, Arvind.
Hi.
Hello. You are at home?
Yeah. How about you? You have come to work?
Yeah, in the office. Yeah.
Are you teaching any course this semester?
Yes, the teaching is over. Now the exam is going on. And in parallel, another semester has started for the first semester students.
Oh.
JEE was delayed 3 months.
Oh, right. Yeah.
So their semester is delayed by 3 months, but it's in parallel with the normal semester.
Okay.
So they will have back-to-back 2 semesters.
Oh.
In fact, 3 semesters back-to-back. Yeah.
Does it mean increased course load this semester for many faculty members?
Or? No, I don't think for faculty it is more. It is more for the students.
Okay.
But this online teaching is not very good.
Especially if you have a large number of students.
Yeah.
Then it can be difficult.
Yeah, it's mainly a formality. The grading, etc., is all fraud.
Students who really want to learn can learn.
Right. But we can, the grading is the part which is questionable.
Yeah.
Learning you can do, sure. Also from NPTEL courses you can learn.
That's correct.
Hello, good morning, Arvind.
Okay, good morning. Is it time or a minute left? Half a minute?
Oh, yeah, half minute, 1 minute. So far, everything is fine.
Yeah. So it's been a wonderful.
Mixing of timings from people from US especially.
Yes.
Because I fixed everything and then somebody says, oh, it is midnight, it is early morning. Because
exactly.
First onwards, I think there was one more change.
So, I think you've organized a spectacular event. Really,
yes.
A lot of hard work you put in. Wonderful. Congratulations to all of you.
Business is very difficult because we cannot fix it exactly.
Yeah.
Europe is easier. After all, it's 4 hours or so. The other one is difficult. Yes.
Yeah. So it's 10:45 now. Shall we get started?
Yeah.
Okay.
Good morning. We have a plenary talk by Professor Nitin Saxena, and I invite Professor Arvind to chair the session. Arvind, please.
It's my pleasure to introduce Nitin Saxena to all of you. He did his BTech in 2002 from IIT Kanpur, and many of you would remember the AKS primality test, which took the scientific world by storm and did India proud. So he started with a paper of dizzying heights. And over the last 2 decades, he has maintained outstanding quality of research and is one of the leading researchers in the world in the field of algebraic complexity theory. a brief overview of his career. He did his PhD in 2006 from IIT Kanpur, student of Manindra Agarwal. Then spent some years in University of Bonn as a faculty member. In between, probably he did a postdoc also after his PhD. Then after five years in Bonn, he came back to IIT Kanpur as a faculty member, where he's currently professor now. He has won numerous awards, including the Bhatnagar Prize 2 years back for his outstanding work. I hand it over to you, Nitin. Looking forward.
Yeah, thank you, Arvind. Thank you for the very generous introduction. And thank you to the organizers for organizing this amazing workshop with great speakers, even in the time of a pandemic. So let me start the talk. This is in the intersection of number theory and algorithms. So this we call efficiently computing Igusa's local zeta function. Now you may not have heard about this function, so I will define it gradually, but it is a very important kind of zeta function. This is joint work with my PhD student Ashish. It was presented this year in ANTS. So, okay. Yeah, so I will start with just this assorted zeta functions and define Igusa's local zeta function. Then I'll go to algorithmic questions. Am I audible and visible properly?
Yes, absolutely.
Okay, sure. And in the algorithmic question about this Igusa's function, I will have to refer to some algorithms which we discovered a few years back. So that I will describe. These will be algorithms for root finding of univariate polynomial modulo a prime power. So mod p square, mod p cube. Okay, so the challenge will really be working mod p to the k versus mod p, because mod p to the k, you don't get a field. And so the roots are very large in number and they are very complex. I mean, it is difficult to describe them. And based on these algorithms, then I'll finish the main algorithm that computes Igusa's local zeta function. Okay, so if you haven't heard about zeta functions, you must have heard about generating functions. And the purpose of this is that if suppose there is an arithmetic function n of k, and you want to understand, you want to collect all these values of n of k for different k's, integer k's, positive integer k's, in one function, which is this g of t. So g of t you should think of as a power series in t. T is a formal variable. Okay, we don't try to evaluate t. T is just a variable, and this is a formal power series. And we think of t raised to k plus 1 as smaller than t raised to k. Okay, so although this series is infinite, it is actually convergent in the power series ring. But this may not be a rational function. It may not be of the form pt over qt for polynomials p and q. Okay. Nevertheless, this function, this power series is very important. This is a very important construction which gives amazing properties about n of k in interesting cases. So generally, it carries very useful information about n of k, and it has been used in all kinds of problems and theories, as you will see here also. So how nk grows decides how this power series converges. So if nk grows very well and if we are able to control the growth of nk, then actually this g of t turns out to be a rational function. If nk grows too fast, then you can show that this series will be convergent in the power series ring. It always is, but it may not converge to something nice. It may not converge to a rational function. And obviously, g of t is never a polynomial. It's a polynomial only when nk is 0 after a point. Okay, so if nk is not 0, if it is positive for all k, then you can see that gt is never a polynomial. So we are really working outside the polynomial ring in the power series ring. So obviously the most important zeta function that you know is the one given by Riemann. So around in 1800s, he defined what we now call Riemann zeta function, which looks a bit different than the generating function. So this is a function of S, and you are summing up 1 over k to the S. Okay, so previously you were kind of summing S to the k in generating function, but here you are looking at k to the S. But the spirit is kind of the same, and you should ask the question, what is this capturing or encoding? Okay, what is this generating function or zeta function encoding? And the answer is that it is encoding prime numbers. Okay, so in a complicated way, it encodes properties of primes. In particular, it encodes it can give you the density of primes. Okay, between 1 to x, how many primes there are. Those results were shown using this zeta function. And obviously, there are many open questions, major questions related to this, which you may have heard of. And this construction or this connection of zeta function with other functions inspired many kinds of zeta functions. So I will not go into the definition, but I'll just name them. So for example, Selberg's function of a manifold, zeta function of a manifold, Ruel's zeta function of a dynamical system, Ihara's zeta function of a graph. So even for a finite discrete object, you can define zeta function like Ihara. This is defined in terms of cycles in the graph actually. And so one point here is that these zeta functions, they are all in characteristic 0. Okay, so you are really working over rationals, or you are working in complex or number fields when you define these. But you can also define these for properties related to finite fields or properties related to extensions of Galois rings. So either Galois fields or Galois rings. Okay, you can also define those functions, and that is called local zeta functions. So the most important one here is what is called Hasse-Weil zeta function. This is related to varieties over finite fields. And the second is the point of this talk, which is Igusa local zeta function. This is for polynomial systems or polynomials modulo prime powers. Okay, both of them, the purpose is to count points. But the first one, Hasse-Weil, this counts points in the finite field extensions, and the second one counts in the Galois ring, in particular integers mod p raised to k. Okay, so let me move forward to the definition, and then maybe you can ask questions if it is not clear. So ZP, by this I will mean p-adic integers. Okay, do not confuse this with Z mod p. This is something else. These are p-adic integers. So the elements here are essentially infinite sequences, A0, A1 to A infinity. These are just numbers between 0 to p minus 1, and then you are summing it up with weight p to the I. Okay, again in this, here you should think of p to the I plus 1 as smaller than p to the I. Okay, so this actually gives you convergent objects, and the convergence is happening in the p-adic ring of integers, or p-adic integer ring. So suppose you are given a n-variate, it's a multivariate integral polynomial. Coefficients you can think of as p-adic integers. So formally, Igusa's local zeta function is an integral. Okay, it is, you want to integrate the p-adic metric of f raised to s. So this should remind you of Riemann's zeta function, but in a very different space. So you are actually integrating this in the space p-adic integers raised to n. So this is the p-adic integer space where you are integrating. this metric raised to S. So this was defined by Igusa in 1900s. So you are integrating using p-adic metric. This is what this F bar P means. And the integration is using Haar measure. I will not define these. In fact, for this talk, you can even skip this because I will give a more palatable definition, more explicit definition in the next slide. So what Igusa and others showed is that this Z of S, this converges to a rational function in Q of P to the S. Okay, so S is a variable and you think of the variable as P to the S, and in P to the S, you will actually get a rational function. Okay, Z of S can be written as A of S, A of P to the S divided by B of P to the S, where A and B are polynomials. Which is a major property from the definition. It is not at all clear why this would happen, because remember that ZP is an infinite space. So this integral is really happening in an infinite space, and then there is no reason why, and this S is appearing in the exponent. So there is really no, a priori, it is not clear why this will be a polynomial in P to the S, because it's really summing up in an infinite series. So Igusa showed this by resolving singularities, and later a slightly more explicit proof was given by Denef using p-adic cell decomposition. But both these proofs are still non-explicit. It is not clear what algorithm do you get. Okay. Nevertheless, they give you the convergence in Q of P to the S. Now, some intuition about this integral. So you can think of this integral in terms of, say, this filtration mod P raised to K. Okay, if you think in those terms, then the p-adic metric for this number P raised to K becomes actually P raised to minus K. So this F of F to the S actually becomes P raised to minus Ks. So what you can imagine here happening is that modulo P raised to K, the number of roots, that is being counted and it is being weighted by P raised to minus Ks. Okay, so you can think of this definition as somehow counting zeros mod P raised to K for all K and then summing it up with weights P raised to minus Ks. Okay, so this is one way you can think of this explicitly, this analytic object explicitly. And based on this, in fact, another definition can be given, which is you define nk of f as the number of roots of f mod P raised to K. And you look at the Poincaré series, P of T. So this big P of T is essentially, it is this NKF, the count, and then for technical reasons we are normalizing it by P raised to NK, and eventually you have this T raised to K to give the formal power series. Okay, you do this for all K from 0 to infinity, positive, non-negative integers. So this is for Poincaré series by this intuition that I just suggested in the previous slide. And
what is n here?
Big N.
Small n.
Oh, small n is the number of variables. Yes, sorry.
Okay.
Right, small n is number of variables. So for this talk, you can also think of small n as 1, because we will be only focusing on univariates later. So, but yeah, in general, n variate, this is n. So, right. I mean, in the ZP to the n space, if you look at mod P raised to K, you have P raised to NK points.
Okay.
So P raised to NK is the maximum number of points. So and you are normalizing by, yeah, you are normalizing by the maximum number of points. Yes. It's kind of the density that you get. in that space. Okay, so let me look at the trivial case, which is f equal to 0, which I just said. So p raised to nk is the full space. So if you look at f equal to 0, then actually this ratio is 1. So you are just looking at sigma t raised to k. And it is very useful to remember that sigma t raised to k for all k is 1 over 1 minus t. Okay, so this is really the connection between infinity and finite representation. So you have seen that p of 0 is a rational function. It's 1 over 1 minus t. And in fact, Igusa connected these two words, the word of analytic definition and this more discrete Poincaré series definition, and showed this identity that PT that PT is equal to 1 minus TZ over 1 minus T. Okay, this is true in general. And you have to think of T as P raised to minus S. So these two objects are actually related. P and Z are related. Poincaré series and zeta function are related. If you take T to be P raised to minus S. Okay, both P and S are variables. So it suffices to now move our focus to P of T, to the Poincaré series, right? Because it is explicit. It is something that we want to understand actually better in computer science. We want to understand this number of points instead of the integral. So now we will only study Poincaré series. Okay. So right, so Igusa's proof actually showed that this P of T converges to a rational function in Q of T. As a function in T, this is a rational function, which is not at all clear from definition 2, because in definition 2, you are again summing up T raised to K with these ratios as coefficients, but the ratios are completely opaque. I mean, you don't understand what is NKF. You don't know that, right? Especially for multivariate polynomials, NKF, how does it behave? So it's not really clear why this will become a rational function from this definition itself. But what it does mean, it does tell you is that NKF must be very special. Okay, there is something special about NKF that makes this Poincaré series converge to a rational function. Because generally power series do not converge to a rational function. Right? For example, if you take coefficient as 1 over k factorial times, and then you multiply it with t raised to k and sum it up, this series will not converge. This will be irrational because, as you can see, this is e raised to t, right? And you can show that e raised to t is not a rational function in t. So almost for all coefficient choices, these series should not converge. So why is Poincaré series converging? That is what we will try to understand in this talk for n equal to 1 for univariate. Current convergence proofs are quite non-explicit. They are analytic, and it is not really clear what algorithm do you get out of them. And so it is also not clear what do they tell you about NKF, especially for small k. So number of points, mod p square, mod p cube, mod p to the 4. So these are the things you would generally be interested in computer science. And it is not really clear what these convergence results tell you about NKF, explicit properties. Okay, so that is what we will now try to answer. We'll try to at least investigate, if not answer. Okay. So the question we ask is, could NKF be computed efficiently? Okay, by efficiently, I mean it should be fast in practice, and theoretically it should be polynomial time. Okay, that's the question. Now, NKF, so as I said before, the number of points is in the space is p raised to k raised to n, so it is p raised to kn. And so you can actually go over all these points, and just by brute force, trivially you can count in p raised to kn time. But then the problem is that as k increases, in fact, p can also be a very big prime, and so even p itself is very slow algorithm. And in terms of kn, it is even worse, it is exponential. So overall, it's an exponential algorithm. So this is not really a practical way to go, but at least there is some trivial way. I also say that much faster than this is actually not likely, and that is because of n. Because if you allow the variables to increase, n to increase, then this problem is known to be NP hard. Okay, even with k equal to 1, if you start looking at multivariate systems, then you get into this point counting becomes kind of satisfiability assignment counting, which is NP hard. In fact, it is even worse, it is permanent hard. Okay, so these problems you don't expect to solve in computer science practically. So what we will do is we will constrain n. In fact, we'll make it 1. So our current question is, could NKF be computed efficiently for univariate f? Okay, x is now one variable. And precisely we want an algorithm that is polynomial time in the parameters, this input f, so degree of f, and the coefficients, which are log p bits. And finally, you are given this p raised to k, so a polynomial in k. Okay, so these are the 3 parameters in which you want a polynomial time algorithm to count the number of points of f of x mod p raised to k. So can this be done? Trivially, it can be done in p raised to k, but what we are demanding is far better than p raised to k. So yeah, right now I have not given you much information except this integral definition. So maybe you can, as a first attempt, try to compute the integral and try to compute this local zeta function z of s. And to compute the integral, maybe you can factorize, you can first look at f of x as a p-adic. I mean, it is a p-adic integral polynomial, so maybe you factorize it, you find the roots. And then once you have this factorization and the roots, you can try to do the integral. Okay, that is conceivable. So to implement that, you have to use a randomized algorithm to factor fx over p-adic integers and find the roots and then attempt the integration. But remember that all this has to be done in p-adic extensions because fx may not have roots in zp. So you have to go to an extension. And in that p-adic extension, you have to compute the integral. So it is not very clear how exactly you will implement this and how fast this will be. But anyways, the starting point is already randomized. So you don't expect deterministic algorithm from this. And you don't expect a very fast algorithm. So our last question, which we will study and solve, is there a deterministic polynomial time algorithm for NKF to compute NKF, where f is a univariate polynomial? Okay, so we will actually go the opposite way. Instead of first computing the zeta function and then from that extracting NKF, we will actually compute NKF, and from that we will build the zeta function. Okay, we'll take the opposite route. We'll go from discrete to analytic instead of from analytic to discrete. And this will be a very fast algorithm, and we will actually learn something new about how NKF behaves. Okay, so right. So next I'll move to the algorithms. Any questions at this point? Maybe it's a good point to ask questions.
I don't know if Vijay, can you unmute the audience to see if there are any, or the chat box at least? Can you open the chat box for questions?
Yes, yes, done. Yeah.
Okay.
So
Yeah, if you have any, sure. If there are any basic questions about definition or what is the problem, what is the history, then you can ask. Details, we will move forward.
I think, Nitin, you can go ahead because there are no questions.
Okay, sure.
People will come in the end.
Yes, sure. So let us then move to the algorithms that we had for other problems and how we will use them in this new problem. So, yeah, so as I already proclaimed that instead of integration, we will take the root of roots modulo p raised to k. And from here, we will go to zeta function. So let the setting is let f mod p raised to k be a degree d univariate polynomial. So coefficients are at most p raised to k and given in bits. Okay, you have this is all binary representation. So Berthomeu, Lecerf, and Quanton a few years ago proved an interesting property for the roots of f mod p raised to k. What they did is they arranged these roots. So first of all, you have to realize that the roots may be a lot. They can be much more than d, because mod p raised to k is not a field. So the roots are not just d many. They can be as many as the size of the ring in the worst case, right? So you cannot really present all the roots in the output because that will be an exponential size blow up. So you need some efficient representation of the roots, and that we will call representative roots. And we will show, it can be shown that they are few and they can be easily represented in the output. So representative root, this is the notation we use. So A0 to AL minus 1. These are again numbers mod p. And you weight them with p raised to I, and then you sum this up. So this is the kind of the truncated part, mod p raised to L. And the p raised to L part, there is a star. So star means that you can put any number there. Okay, star means it's a wild card, so you can put any number. And so you should think of this bold A as a set. Okay, that is the correct way to look at it. But I will think of it as an element. It's for me, it's just a representative root. So as I fix star, I get different roots. Okay, so exponentially many roots are represented in this bold A representation, which is very compact. It only requires L numbers A0 to AL minus 1 to describe. The property of this is that it should be minimal, and that it itself, I mean, everything in this should be a root of f. Okay, so everything in bold A should be, f should vanish at this, and you cannot make L to L minus 1. Okay, so you AL minus 1, not all AL minus 1 will work. If they work, then we would have put a star there. Okay, so that is what I mean minimal. So this will be a minimal representative root. I mean, representative root will be minimal and everything there will be a root. That is the definition. Now, BLQ result is that all the roots, the set of roots can be can be partitioned into representative roots. And the number of these parts, these representative roots, is at most D. Okay, which is an amazing result because it is telling you that in some way you are getting the finite field result, that in finite field there are at most D roots, mod p raised to k, there are at most D representative roots. Okay, so we are kind of recovering that fundamental property of polynomials over fields, except that we have to move to representative roots, and which have a compact representation. This proof is inductive. In fact, in 2 lines, I can give you the idea of the proof. It is based on the transformation. You basically, what you do is you try to iteratively build the root or build some root of f. So say you have built it up to m minus 1. So here you have a0 to a m minus 1. And the remaining part, you call it unknown. So it is x. X is the unknown. Okay, so you have this known part in red plus x times p raised to n is the unknown part. Now f at this, you know, is 0 mod p raised to m. So you have built up to p raised to m, and you want to reach up to p raised to k. So, so this f evaluation is divisible by some power of p, at least p raised to m, but maybe more. So let us call that v, valuation of this f evaluated. And if you divide by p raised to v, then now it is non-zero mod p, right? So you call this g of x. So you remove the extra p's, what remains is g of x. And to find x, what do? You find the root of gx mod p. Okay, so root of gx mod p will give you am, which is progress. That's the induction step. So from m minus 1, you will reach am. And in this way, you have reduced the characteristic p raised to k root finding to characteristic p root finding. Okay, so it's basically this reduction to finite fields. And when you formalize this idea in a proof, you will get representative roots. Yes, okay, and then you continue with now sigma ai I0 to im. And at some point, this process will stop, and what you will get is a representative root. And why are these few? Why are the representative roots few? That is a deeper property. I will not go into this because I don't think I have much time left now. So, but this is the key idea, and you can build on this. It's a cute and useful set of 3 lines that you should remember. Okay, so based on this, yeah, representative roots are few, but remember that each representative root is representing exponentially many roots. Okay, so the roots are exponentially many, but the representation is small. For example, look at the polynomial p times x, mod p square, right? So x can take any value, any multiple of p, and you will get a root. So you have actually p roots. And what is the representative root? Or what are the representative roots? So it's actually trivial here. There is only one representative root, which is 0 plus star p. Okay, so 0 is the known part, and then the remaining part is actually star. You can put any integer there, and that times p is a root of f. And these are all the roots. There are no other roots. So this is the single representative. Okay, this is how you get the connection to representative roots. So based on this, actually, the BLQ gave a fast randomized algorithm to find all the representative roots, and hence all the roots mod p raised to k. And once you have this result, you actually counting is also easy, because representative roots, how many roots it represents, you can easily count. It represents p raised to k minus l roots, right? So you just have to sum up over all p raised to k minus l. Because it went till L minus 1, I was till L minus 1, and then the P raised to L was with a star. So star will take P raised to K minus L values. So that is the number of roots it represents, and then you sum up over all representative roots. That gives you NKF, the number of points mod P raised to K. Now, so that is great progress. What remains is to make this deterministic polynomial time. Okay, and that is one question. The other question is, this theorem has still not given us much information about NKF, the structure of NKF, the function NKF, right? So it tells you that NKF can be written as sigma p raised to k minus li over all the representative roots. But then what are li's? It doesn't tell you that. So it doesn't tell you much about the Poincaré series. NKF is still a mystery because li will depend on I and k. So for every NKF, it will be a different thing, and you will still not be able to sum up the infinite series. Okay. So subsequent to that, what I did with Dwivedi and Mittal in CCC 2019 was we made this algorithm deterministic. Okay, we made it deterministic polynomial time. So these details let me skip because we don't have time now. But even after all this, NKF remains a mystery. So we do get a deterministic polynomial time algorithm to compute NKF, but then this is still not enough to compute the Poincaré series because Poincaré series will require infinitely many NKF, right? So that you cannot really do. Okay, so what is the solution that we propose? So the solution basically arises from this intuition that NKF, which we have written as over representative roots, this p raised to k minus li sum, this should behave better for large k. Okay, as k increases, as k tends to infinity, this should become somehow standardized. The intuition is that because you are getting close to p-adic integers, right? Large k is like studying roots in ZP, and ZP is an integral domain. It has a field. It is contained in a field. So in the field, you know that a polynomial f, this polynomial f cannot have more than d roots. So in particular, NKF cannot be more than d. So at that point, it will stabilize. Okay. So for large k, this will stabilize, and then kind of NKF will become constant, and so you can intuitively feel that the Poincaré series will converge to a rational function, right? But this has to be formalized. When will NKF become well behaved? At what point? And then can you actually compute Poincaré series exactly? So those questions we answer, but this is the basic intuition. So what actually we show is that for large k, Li is linear in k. Okay, we show Li, we give an exact expression for Li as a function of I and k. In particular, in terms of k, it is just a linear function. And since the function is explicit, we can sum up the Poincaré series. That is the whole algorithm. Okay, the idea of the whole algorithm is actually just this line. Let me just give you some more formulas if you can remember. So the point when NKF becomes good, it becomes stable, well-behaved, is K0. K0 depends on the degree of F and the discriminant of F. It's actually discriminant of radical of F. You could think of this as look at the p-adic integral roots of F and the differences alpha I minus alpha j of the roots and take the product. So what is the p-adic valuation of this product? Okay, based on that and based on the degree, you get K0, explicit bound. And LIs, which appear in NKF formula, LIs depend on, it's actually K minus valuation divided by the multiplicity of these alpha i's. Alpha i's are p-adic integral roots of F. So based on the multiplicity and based on the valuation of part of F on alpha I, you get LIs. And these two formulas then give me all I wanted for NKF. Okay, alpha i's are all p-adic integer roots. By the way, these I will not compute. I don't need to compute alpha I in the algorithm. This is only theoretical. Okay, but I will only compute NKF. And from NKF, I will deduce everything. and I can actually sum up the Poincaré power series. One interesting corollary of all this is that if f is square free and k is larger than k0, then actually NKF becomes independent of k. Okay, so the basic intuition is actually correct up to some point. Basically, you have to assume that f is square free. If f is square free, then NKF after a point becomes stable. It is actually constant. It doesn't change with k.
Nitin, is that Fi F? You mean F of alpha, no?
No, actually, Fi is the part which is co-prime to x minus alpha I.
Or the factor of F?
Yes, factor of f. So from f, you remove
okay.
maximum x minus alpha I.
Okay.
What remains? Actually, that is the problematic part. So if that was not there, or if its valuation was 0, then its contribution is 0 here in this formula.
Okay. So that is what is contributing to the multiplicity of the representative root.
Multiplicity is the second problem. Yeah, both these are problems. So the remaining valuation is the problem. So that you have to subtract from k, and the multiplicity is a bigger problem that you have to divide.
Okay.
K should be divided by that. So these are two different independent problems, and this is why this analysis is not direct. It creates counterintuitive problems. But yeah, Li, we actually pinpointed to be this, and from this I can say that when multiplicity is 1, then you can see that K minus Li will become independent of K, and NKF then ultimately becomes independent of K. So you can immediately feel that the Poincaré series will converge, and it converges in general. We can compute it. So that's the last slide. So now I know that NKF looks like sigma p raised to k times ui, where ui is that expression that you can get from the details, and k you are assuming bigger than k0. So for these NKF, you have the exact expression, and when you put it in Poincaré series, what you will get is this red part, p raised to k times ui minus 1. So it is something like sigma p raised to k times t raised to k, right? Which is 1 over 1 minus pt. So that is a rational function. So you get a rational function here very explicitly, and this is all deterministic polynomial time. Okay, so let me stop at that. So infinite sum, again, I learned that it converges to a rational, but this is all steps are explicit. And our algorithm actually computes the Poincaré series, NKF, and then the Poincaré series in deterministic polynomial time. Okay, so yeah, let me just wrap up 1 minute. So, so we give a deterministic polynomial time algorithm for Igusa's local zeta function. But remember that it is only for univariate polynomial. Okay, so we don't even know what happens for bivariate polynomial. We cannot be too ambitious. Number of variables, as they increase, this problem will become permanent hard or NP hard. So we cannot hope to do anything there. But at least bivariate, trivariate, we should try to generalize these methods or find new methods, because we hope that there should be polynomial time efficient algorithms. So what can we do for bivariate? And their relevant questions are, how do you estimate the number of points? So f x1 comma x2 mod p raised to k. What is the number of points? That understanding. And from there, you can generalize to counting factors. So why just count roots? Can you count factors of univariate f mod p raised to k? Right? This is also an open question. In fact, even checking irreducibility of a polynomial mod p raised to 5 is currently an open question. There is no practical algorithm known for this. Okay, no randomized, no heuristic algorithm is known to even check whether given f is irreducible mod p raised to 5. So counting factors is a harder problem by current standards. But there is no NP hardness results, and also we don't believe there to be one. Okay, thanks.
Thank you. Great talk. Questions from the audience? Maybe they'll come up with a question. Meanwhile, I'll ask one.
Sure.
What is the bound on K naught in terms of the degree and P?
Yes,
Is there a nice bound on K naught?
Yeah. We give in the paper, yes. In the paper, in the second page already, we give it because this seemed like something new. So here you can actually calculate when I get this. Sorry.
Discriminant.
Yeah, so discriminant will be something like P raised to D or maybe P raised to D square.
Okay.
And so the valuation cannot exceed D square. So K0 is like D cube.
Okay.
Yeah. In fact, I think it's better. What we give in the paper, it is D square times the magnitude of the coefficients of F. Log of that. Yeah, so it's roughly quadratic in the degree. So K0 is quadratic, and that is why the Poincaré series degree bound is also quadratic. So you can write the Poincaré series as AT over BT, where AT is degree around D square and BT is degree around D. So quadratic over linear. It's very explicit, yeah. Which is not at all clear from any of these definitions or analytic proofs.
Yeah. On your last slide,
yes.
Is anything known about, so if I pick a polynomial f at random over the p to the 5, z mod p to the 5 Galois ring, is it irreducible with high probability?
I think so. Oh. Yes. Probably we can prove it, yeah, but I cannot prove it now.
No.
But I think you can prove that randomized polynomials will remain irreducible as what happens mod p. Yeah.
Now I was wondering if it depends on the exponent 5. As you go modulo p to the k for larger and larger k, does the number of irreducible polynomials shrink? That is of some degree. So you take degree d and does it shrink, or what is your intuition say?
So if you go all the way k infinity, then you get to p-adic integers, and which is the like you are in a field now. So the field, whatever you expect,
should be dense.
Yeah. So in a field, you will get the probability to be 1 over d.
Okay.
Right. The density will be 1 over d. So that, anyways, in the limit, Okay. Here in p raised to 5 and p raised to 4 and p raised to 6, these small powers, the problem is the field methods don't work. So even to prove or even to find the density of irreducibles, you have to give a different proof. Yeah, you have to give a more complicated proof, but it should be possible, I think. Especially by our methods, because we have developed some methods to factor up to p raised to 4.
Oh, okay.
So I think by all that, it should be possible to get a probabilistic bound.
Any questions from the audience?
I think Ashish must also be there in the participants. So people can talk to him later. Hello, Ashish.
Hi.
Yes. Yeah.
Okay, one final question maybe before we wind up. I was wondering for univariate polynomials modulo arbitrary composites.
Oh, yeah.
Say many prime factors.
Yes,
Is the problem hard?
Yes. Yeah, I mean, that is exactly the question of integer factoring.
Okay. Oh,
yeah. So finding square root of, or factoring x square minus a.
Oh, yeah.
Right? X square minus a mod n.
Yeah.
Then you break all internet security. So it's a very important problem.
Yeah. Correct.
Yeah.
Okay, great.
Okay.
Thank you. Thank you.
Thank you. Bye.
Okay, over to you, Vijay.
Thank Thank you, Professor Arvind and Nitin. We will resume at 12 noon for the 12th plenary talk by Koji Matsumoto. Same link. Thank you.
Thank you.
Thank you. Bye.
Bye.